Hello people, what's up? क्या चल रहा है? So unlike the other videos, this time I do not have a fact to start off with because the most interesting fact is I've not made any videos from the last 2 days because it's freezing cold here. It's like 4 degrees right now, and so that's the reason we are hanging out more in Kambal. And yeah, and if you see my voice hanging today, so you certainly know why is it so. But yeah, let's get started. So we'll be studying about rate limiter today. And as usual, this person took zero effort to make a new page rather than just did this thing that I always do. तो चलो शुरू करते हैं. So what is a rate limiter? So rate limiter, as the name suggests, is a system that helps you limit the rate. But the rate of what? The rate of request calls. So what happens is you have a client, right? And then there's a service. So client can make some request to the service, okay? But these requests cannot be unlimited. There has to be some upper limit within a particular time period that tells you, okay, this is how many requests you can make. For example, this is not the exact number, but just for an example, say on Instagram, you cannot make more than 2 posts per second, or using the same IP address in a day, you cannot create more than 20 accounts. Because why are we doing so? Like, what's the use of it? Because what it helps is it helps your servers from not getting overloaded. So basically, there might be some user who's having suspicious behavior or misbehavior. So in that case, he or she may send out excess request. When we say excess request, it means like maybe creating 100 accounts in a day using same IP address. In that cases, you use a rate limiter and that helps your server from being overloaded. The second is reduce cost. So when you limit the excess requests, so that what that means is you are now using fewer servers because you are saving on the servers, right? By controlling the number of requests. So this helps to reduce the cost. This prevents your server from getting overloaded. And the third being, it prevents the resource starvation that is caused by denial of service attack. When it happens is when a particular user or a particular system is overusing the server so much that others are not getting to use it. So what happens is denial of service happens. So what it happens is it prevents resource starvation, that one user is not being able to access anything only because one other user who's doing misbehavior is essentially making unlimited API calls. So step one, when we build a rate limiter or when say we are in an interview, so this is basically the flow that book takes. So it assumes that it's an interview setting. So that's how you go about with your interviewer. So you essentially understand the problem and what is the design scope. So what you essentially ask is for whom am I making this rate limiter? Is it for a startup or is it for a big company? How it helps is because it helps to understand the scalability, the stuff like scalability, as in the last video we discussed about back of envelope estimation, right? So based upon what the scope of the company is, you essentially design your system that way. And the other question can include something like where would this rate limiter be? Would it lie on the client side or would it lie on the server side? So majority time we make sure that it lies on the server side because we have the control there. Client side we don't have much control. So asking all these questions helps you build a set of requirements. So what these requirements look like, that what is the latency that the system can tolerate due to the rate limiter, and then do we need a distributed rate limiting? If so, then what is the estimated load a server would take, and etc etc. So yeah, this is about that. आगे चलते हैं. So yeah, as I just discussed, that where to put the rate limiter is a very major question here. So that's your client and that's your server. So what we prefer is that we put the rate limiter on the server side. Why is it? Because we may not have the control over client implementation. So essentially, since we have the control over the server side, it's preferable to put the rate limiter on the server. But besides this approach, the client server side rate limiter implementation, there's a better way that you can create a rate limiter middleware. So what it means is you put it in the middle. So basically, okay, we'll discuss it later. So if there's a scope, then only it goes to the server, else the requests are dropped. So it's more like that's alternative way. So instead of putting the rate limiter at the server, what you do is you create a rate limiter middleware which throttles request to your APIs as shown in the photo. Okay? So this is the example that they gave. For example, your API, this API allows only 2 requests per second. Okay. So what this will do is at this layer only 2 requests would be allowed to go. The third request would be dropped here only rather than going to the server and getting rejected here. So when we talk about rate limiting right now, it might seem like very abstract, as in hota kya exactly, how do we implement rate limiter? Thumbs that have been designed. We'll go through them one by one. So the scope here is not essentially understanding what these algorithms are. I mean, obviously that is one thing, but the majority thing is how do we take the final decision ki which algorithm am I gonna use finally, because it's like system design that we are discussing. So it's like we discuss pros and cons of each of the algorithm, and based upon that we realize ki theek hai, shayad this is something that I need to go ahead with. So let us start with the first algorithm, that is a token bucket algorithm. So token bucket algorithm is like a very widely used algorithm when it comes to rate limiting. So this is one algorithm you can remember. So Stripe, Amazon, everyone uses, not everyone, Stripe and Amazon both use token bucket algorithm. So what it essentially means to have a token bucket algorithm is that very from the name it's clear, token bucket. So there is a bucket that has got some tokens. So now this bucket has a predefined capacity. That, for example, in this case, if you see the capacity of this bucket is 4. So what happens is there's a concept of refiller. So what refiller does is every second, like this will define later as in what's the time the refiller comes in and fills. But what essentially happens is after every timestamp, the refiller comes and put some X tokens back into the bucket. So essentially your bucket gets refilled every time, but the bucket capacity is limited. So let us try to understand what happens here is. So there's a bucket. This bucket has some set of tokens, and now since this happens after some X seconds, as in the refiller refills it, so when a request comes, if it sees that there are enough tokens, as in there's a token in the bucket, the request goes through. It gets reduced by 1. But when say a request comes and there's no token in the bucket, this request doesn't go through. But after some X second, this will get refilled. So at that time, this request will go through. So that's what they write here exactly. If there are enough tokens, we take 1 token for each request and the request goes through. If there are not enough tokens, the request is dropped. So when will request will be dropped? This request will be dropped when in a time that's less than 1 second, more than 4 requests comes. Because the refiller does refill after every 1 second, right? So when will this case happen? That refiller has already refilled at timestamp t00, but more than 4 requests has come between t and t.01. Like the refiller has not refilled, but these are also empty. So yeah, so that's the design of this, a set of requests. Each request comes through, it checks, does bucket have token? If yes, the request goes through. If no, the request is dropped. So now when we say the request is dropped, so there might be 2 ways out there. Either we completely drop the request or we temporarily store it in some place so that when we have enough tokens in the bucket, we process them. And with a very nice example that they have here, that let us assume that the token bucket size here is 4 and the refill rate is 4 per minute. Okay, so what you need to remember is bucket size is 4 and what is the refill rate? Refill rate is 4 per minute. So what happens here is, if you see, this is the timestamp 1. So this 1 is just like you can assume as in it's the timestamp, as in I guess we are clear. So this is hour, this is minute, this is second. So initially we start with the 4 tokens. The first request comes, it goes through. What happens? 1 token is consumed. So now this request came at 1.5. The first request came at 1 and then 3 requests come at 1.5. So notice that 1 tokens refilled, next token will refill at this time. As in after 1 minute. I'm sorry. Yeah, it refills now. Here. So all the requests that come here need to survive with these 4 tokens. So these requests that are here, what they do is they consume all the remaining 3 tokens. So after 1.5, what happens? The size of your bucket goes to 0. So any request that comes between this time to this time is gonna get dropped. So what happens is from this till this timestamp, nothing goes through because your bucket is empty, and then at 1 the refiller comes again and now the request will go through again. So the point here is when you see for different scopes, you will need different buckets because not for everything it will be same, right? For example, the user is allowed to make 1 post per second in case the bucket size will be 1. And then if the user is required to make 150 friends per day, so isme the refill rate would be 150. And what would be the timestamp of the refilling? It would be per day, as in after each day 150 gets filled. And what would be the bucket size? Bucket size would be 150. So you will need to have different buckets, each for a different use case. So when we talk about this algorithm, do you see what the issue with it is? I mean, it's easier to implement algorithm. You just need to, tune the token size, the bucket size and the refill rate. But what's the issue with this algorithm? The issue here is that it might be possible that at one instant, at the start only, all the request comes and they consume the token and then nothing happens after that timestamp. For example, just to explain the case, this is when it gets refilled, right? This is when it gets refilled. And then this is the start. Right now, bucket has 4. Right now, the bucket has 4. All the requests come in this 1 millisecond, consume all the tokens, and then nothing happens here. Nothing happens here. So that's the issue here. So yeah, the algorithm is easy to implement, it's memory efficient, and it allows a burst of traffic for short periods, and request can go through as long. वैसे I'm not saying why is it, I don't think it should be a pro, but ठीक है, हाँ, so it allows burst of traffic, but I guess they'll tell about this in this algorithm as far as I remember. Huh. So let us try to address this. Let us try to address this thing. So then there comes a leaking bucket algorithm. So what a leaking bucket algorithm does is, so let us see what was the issue there, right? We did understand that. So what if when the request come, rather than instantly consuming a token, if I can store all the request in a queue and then process it till the time we have tokens. In that case, this situation won't happen, that the request came in a very short period and they consumed all the tokens and then nothing happens for rest of the minute. So system is not overloaded for just that period. So that's where we talk about leaking bucket algorithm. So let's just read. It will be just easier to understand. It's similar to the token bucket, except that the requests are processed at a fixed rate, unlike the last algorithm. It's usually implemented with the queue, FIFO queue. So what happens is, when a request arrives, the same thing happens. It checks if the queue is full. If the queue is not full, it stores the request in the queue. So now you have a queue separately for request. And say the queue is full, the request gets dropped. And now what happens is, at regular intervals, it takes the request one by one and processes them. So essentially, for a particular timestamp t, for 1 second, it will just process these number of requests that are in queue. So essentially, there would be a upper cap on the number of requests that are processed. So it takes two parameters. What it takes is, it is equal to the queue size. So here bucket is our queue. And outflow rate, how many requests can be processed at a fixed rate. So what is the best thing here, that the requests are processed at a fixed rate, unlike the token bucket algorithm, where it was happening that in 1 millisecond all the requests were getting processed. But what's the issue here? The issue here is, we have a queue, right? So till the queue size is, till the queue is full, you don't allow any new request, right? So what will happen here is, suppose we get a request 1, 2, 3, 4, 5, 6. So greater the timestamp, the recent the request is. So these fill the queue. Right now, these are filling the queue. And suppose these are taking enough time. So what will happen is, all the new requests will keep on getting dropped, because nobody will get a chance to process, because the queue size is already full. But there are two parameters that you have to tune here. Unlike the last algorithm, where you had the refill rate equal to the bucket size, here you need to tune what's the outflow rate of the request, and also you need to tune what the queue size is. But the only issue that it fixes is that it processes at a fixed rate. So let us study about, so right now what we are doing is, we are going through each algorithm, understanding what pros and cons is, like thinking that way. Once you know the algorithm, you think iska kya fayda hai and iska kya nuksan hai. Let us go through the other algorithm, that is fixed window counter algorithm. So what it essentially does is, as the name suggests, that there's a fixed window, as in for a timestamp, it specifies the number of the requests that are allowed, like it assigns a counter to them. So what happens is, for example, if this is my time scale, let me divide it into some buckets, and then each section has a counter. Each time a request comes, and if it falls into this counter, this counter is incremented. And then once the counter reaches a threshold, all the requests are dropped until a new time window starts. So yeah, this is a very nice example here. So the time unit here they took is 1 second. So each second has got a counter. The counter value is 3 here. That maximum of 3 requests is allowed. So as we see here, the green means that the request was successful, and the gray means that it was rate limited. So we see that at the first second, all the request goes through, but at the timestamp 1, we see out of 6 only 3 goes through, because max 3 can go. But when you see this, do you realize that this has got a problem? Like, what can be the problem here? You have a counter for each timestamp. So now here it is rate limited, the problem that the second algorithm was following. And the first, yeah, it's easier to implement as the first algorithm. For each timestamp you got a counter, and then also you have a upper limit on the number of requests you can go through. The issue here is, imagine this case. So right now this will be about per second. Let us take example of a minute. It will be easier to explain here. So now each minute we were allowing 5 requests, है ना? So right now, is there a problem here? No, right? In this particular 1 minute, 5 requests went through. In this particular 1 minute, 5 requests went through. But if you realize, from timestamp this to this, let us say for simplicity, this is 2:00:05, and this is 2:01:05. So this is total 1 minute. How many requests went through? 10. This is against the policy, right? This is not rate limited. Too many requests went through. But this condition was getting satisfied. So essentially, this is the issue here, that for the 1 minute window between this and this, 10 requests went through, and that was twice as many as that. So when we talk about this algorithm, the pros here is that it's easy to understand. Each timestamp has its own counter, and then you are able to reset the counter after every window. But what is the bad side of this algorithm? That at the edges of window, you are allowing more requests than that's allowed. So there's a spike. So there's a spike at edge. Then the other algorithm is, so the point here is not again saying not learning what the algorithm is, but once you know the algorithm, seeing what are the bad parts of this algorithm and what problem it is solving. So simply when I tell about the issue with this algorithm, what is the solution that you approach to it? That rather than doing the counter voice thing for each timestamp window, how about I just store the last timestamp when I got a request? So this way what will happen is, if I store the timestamps of the request, whenever I get a new request, I'll have some timestamp T, I'll have some timestamp T old. So I can simply check how many timestamps lie between T old and T1. So this will just let me know ki, okay, I can't let go through this request even if it is in a new timestamp window, because there's still an overlap. So that's what sliding window log algorithm does. What it does is it keeps track of the timestamp as well. So the solution I explained here is exactly that's written here. The algorithm keeps tracks of the request timestamp. When a new request comes in, what we do is we remove the outdated timestamp. When we mean outdated, what is outdated? T minus the timestamp window. Because we only care about the timestamp window, right? As in the last example, the timestamp window was 1 minute. So I'm just going to clear about all the requests that came before 1 minute, because what I care about is how many requests came up in just 1 minute. What we do is, for the new request, we add the timestamp to the log, and if the log size is same or lower than the allowed count, we allow it to go through, else we break it off. So that's exactly explained here. The timestamp comes, we store it in the log. It comes at 1 second, we store it. It comes at 30 seconds, we store it. Since the max allowed is 2 here in this example, if you see here max allowed is 2, the one at 150 comes, we don't allow it. Why? Because we check the log size. We check the log size between 150 and 00 I guess 50, total 1 minute. We see the log size is 3, we don't let it to go through. Then the timestamp at 140 came, we simply remove all the logs that are before minus 1 minute, that are all after 1040, so that are before 1040. So this one gets removed, this one gets removed. We check the log size, yeah, and we get it through. So basic point here is that unlike the last algorithm, here we also maintain the count of the last timestamp to make sure that not just in the timestamps defined, in any timestamps we should not get more than X request. I'm sorry if I'm bad at explaining here, but I hope you guys understand. Back in this video, I'm gonna attach the link to this book also, so that you can read through it and then it will be very easier for you to understand what I was trying to explain then. Then when you see this algorithm, what's the issue here? Everything is sorted, right? It's easier to implement. Why? Because you just need to store the timestamp. The upper count is maintained. How? Because at time t, if a request comes, you just check how many timestamps are there between time t minus t minus 1. If they are more than the given count that you're allowed, you simply drop it, else you allow it. The issue here is, since you are storing timestamp of every request, it will cost you a lot of memory. Although you are discarding or removing the timestamps after your limit, what if your t limit that you're considering here 1 minute, what if it's very large? So there will be a lot of timestamps that get stored, because you're storing the timestamps of the requests that are going through and the ones that are getting dropped. So yeah, pros that it's very accurate and any request will not exceed the rate limit. Cons here that you are storing all the timestamps. So I guess enough about algorithms. I guess there's one more algorithm. So what happens essentially there is, it just does one more computation, that it also considers the overlap. So when you consider about the current time, it considers how much overlap is with the previous timestamp, and if the request should go through or it should not go through. So it is request in the current window plus the request in previous window plus how much overlap. It solves the same issue as this algorithm, the issue that was happening here. So I guess we're done. I guess it's very clear, but how it helps here is that we don't need to store the timestamp here, because it's the computation that we do on the go. So it's very memory efficient. It's just that the implementation is a little complex here. Level architecture when we design a rate limiter now. So now we know what is the algorithms that are getting used here. So we have got a full clarity over here. I'll recommend you reading the algorithms one more time. You'll get much more clarity than me explaining it. So the higher level architecture is कि you have a client, you have a rate limiting middleware, and then you have the server. So what happens is the client sends the request, say R. So what it does is it fetches the counter from the Redis. What is Redis? Redis is an in-memory database. It is same as saying you fetching counter from the place where you have stored. So disk reads are, heavy, as in we discussed it earlier when we were doing back of envelope estimation, that memory reads are much faster than disk reads. So you refer to the Redis, you get the counter from here, you check if the counter is less than the threshold. If yes, you let your request to go through, it goes to the API server. If not, you just drop the request. And when in the earlier case you were letting the request to go through, you increment the counter by +1 and this update goes to Redis again. I hope this is clear. आगे चलते हैं. Oh, what is this? So this is more like design deep dive, that when you design a rate limiter, you need to also design some set of rule. These are rate limiting rules. So I guess that this is just example of some component. I don't remember exactly. So Lyft, yeah. So Lyft is basically a community. It open source their rate limiting component, and this is how their config looks like. So what it means is they allow a maximum of 5 messages per day. What is unit per day? How many? What is the threshold? 5. Same here. They allow a maximum of 5 logins per minute. So that's how you define your counters, that's how you define your timestamps. But the point here is, when we were talking earlier that when we're talking here, I guess upar tha na wo diagram. So when we were talking here, what is this? So whenever I send a request, what if I don't just get to know what happened? I should at least get some message, right? That this request was forbidden because I made too many requests. Or maybe a safer side would be saying, whenever I make a first request, I get a message back saying ki, suppose this, I get a message back ki there's a particular limit. And then these are only number of requests you can make ahead. So this will help me better manage my requests. So that's what exactly the book talks about here. Not the book, Alex, Mr. Alex. उन्होंने book लिखी है. So that's what exactly here, X rate limit remaining. So it tells you that given the window, as in for the next 1 hour, these are the number of allowed requests you will be make. And then, or it may be before you start, it gives you a notification saying that in 1 hour, you can just make 5 attempts to log in. I guess this is very same as whenever you try to log in into YONO SBI, वो पहले बोल देता है कि 3 attempts remaining password पे, है ना? तो yeah, that is something we are talking about. So abhi, since we have read so much about algorithms, read so much about the complete, what is rate limiting, design kaise kare, what are the algorithms, why do we need it? Let us now very nicely understand what the detailed design is. So what happens is, इस डायग्राम से शुरू करते हैं. What is this diagram? I'll try to explain this. Rules are stored in disk. तो होता क्या है? Rules. What do you mean by rules? I already explained what rule means. This is rules we are talking about. So rules are stored in disk. So workers fetch करते हैं rules disk से. Since rules are not updated that frequently, like once a service define a rule, I guess they just remain unless and until there's a design change or something they talk about. So once this is done, you store it in cache. Why? Because disk reads are heavy, as I said. तो हमें इतना पोर्शन तो समझ आ गया इसका, है ना? इतना भी समझ आ गया कि रूल्स कैशे में स्टोर्ड है. सो व्हाट हैपेंस इज, दिस इज क्लाइंट, ये तो हमें पता है. क्लाइंट मेड रिक्वेस्ट, दिस रिक्वेस्ट वेंट टू rate limiter. What this rate limiter does is it asks the cache ki what is the counter, as in what is the counter that I have. So now here your rate limiter knows what the counter is. Let us just erase this. So now the rate limiter knows what the counter is, how many requests I am allowed to go through or something. So now when a request comes, it sees, so it knows the max 5 I can do. Now what it does is it checks what is the current counter value. So this is upper limit, right? This is fixed. What is the current counter value? How many requests I have already achieved? For this, it inquires Redis. Redis stores your current counter value. Redis stores your current counter value. It sees if, let us say it has small c and capital C. This is fixed. It sees if the c is less than c. It can let this request to go through, as in it goes to the API server. Else it needs to tell that too many requests. And whenever this path happens, the counter needs to be incremented by 1. So this update again goes to Redis. And now, so let us just highlight this. I guess we understand होता क्या है. आप rules read करते हो, workers rule read करते हैं. क्योंकि rule इतनी जल्दी अपग्रेड नहीं होते, आप उसे कैशे करते हो. Then आपका जो rate limiter है वो कैशे से read करता है कि max कितनी request allowed है एक particular time stamp में. It has that counter C. Then it maintains it ऑन काउंटर छोटा सी दैट इट स्टोर्स इन रेडिस अगेन. कैशे हियर कैन बी एनीथिंग, वो बाद में डिस्कस करेंगे. देयर इज अ सेपरेट चैप्टर ऑन कैशे जितना मेरे को याद आ रहा है. रेडिस से रीड करता है. अगर योर काउंटर इज लेस दैन जो स्पेसिफाइड काउंटर है, जो रिक्वेस्ट है वो पास थ्रू करती है. अगर नहीं तो रिक्वेस्ट कैन गेट आइदर द रिक्वेस्ट कैन गेट ड्रॉप्ड और इट गेट स्टोर्ड इन द क्यू कि बाद में प्रोसेस हो जाएगी. ठीक है, तो आई गेस वी आर क्लियर. और हमने गन तो बहुत ज़्यादा मार दिया, जिसे थोड़ा क्लीन कर देते हैं. माना हमने अच्छे से पढ़ा है बट हाँ ठीक है. सो अगेन आई हाईली रिकमेंड कि आप इसे जाके रीड करो, बट आई जस्ट रीड इट फॉर यू रियल क्विक. The rules are stored on the disk. Workers pull those rules. When a client sends request is sent to the rate limiter. Rate limiter load rules from the cache. It fetches counter and the timestamp. If the request is not rate limited, it is forwarded to API server. If it is rate limited, it returns 429 or maybe stores it into a queue. Exactly what we explained here. कभी कभी लगता है अच्छा समझाती हूँ. चलो वेरी क्विकली अब देखते हैं कि अभी जो किया ना ये सब, इट वॉज अ सिंगल सर्वर थिंग. But what happens in a distributed environment? Because, building a rate limiter in a single server environment is not difficult. The issue that happens in distributed environment is, suppose there are multiple servers, okay? There are multiple servers here. तो जब आपने, तो what happens here is, original counter value मान लेते हैं 3 है. The first request went to server 1, the other request went to server 2. Both of them read the cache simultaneously, as in Redis को दोनों ने simultaneously पढ़ा. They realized, okay, the counter value is 3. It is less than the desired value 4. Both of them let go through the request. But actually what happened was, this also increased the counter by 1, this also. Actual counter value should have been 5 because it was already 3 and then you incremented by 2. But both of them updated it to 4. So इसका सॉल्यूशन इज देयर, एज इन इफ यू हैव गॉन थ्रू डिस्ट्रीब्यूटेड सिस्टम यू विल से हाँ ठीक है लॉक्स यूज़ कर लो, ये सब यूज़ कर लो. बट या दिस इज अ प्रॉब्लम दैट राइट नाउ वी आर टॉकिंग कि ये इशू होता है. एंड द अदर इशू इज सिंक्रोनाइजेशन इशू. सिंक्रोनाइजेशन इशू क्या होता है कि रेट तो बेसिकली सपोज 2 क्लाइंट्स है, क्लाइंट 1 एंड क्लाइंट 2. अपने अर्लियर सेटर में देर वॉज ओनली अ सिंगल क्लाइंट. सो नाउ क्लाइंट 1, so there are 2 rate limiters also. So client 1 sends the request to rate limiter 1 and client 2 sends the request to rate limiter 2. And now both of them increase the counters. Hana, this has a counter 1, this also has a counter 1. But in the next request, client 2 ने अपना request भेज दिया rate limiter 1 को. Since rate limiter 1 is not aware about client 2, it will treat it as a new client, right? और वो उसका counter initially 0 रख देगा दोबारा. So do you see what the problem here is? So that's a synchronization issue here. Again, इसका भी solution क्या है कि दोनों rate limiters they'll first query a common database where इन दोनों का data store होगा and from there they'll respond. But right now again it is the problems that we are talking about. Solutions we always have. So yeah, rate limiter 1 does not contain data about client 2, thus rate limiter 2 cannot work properly. The solution is to use a common database. So I guess that is it. The last and the major point here is after the rate limiter is put in place, it's very important that there's a continuous monitoring that you do throughout. For example, as in if your rate limiting algorithm is effective or if there are some set of changes that need to be made. What do we mean when we say some set of changes? That you realize, okay, I need to maybe change my counter value or maybe I need to make my counter more strict. So that's what is essentially monitoring. तो आई गेस काफ़ी बड़ी वीडियो हो गई है एंड मैं भी थोड़ा थक गई हूँ बोलते बोलते. तो अपन रैपअप करते हैं. अपन ने क्या रीड किया क्विकली गो थ्रू कर लेते हैं. इट वॉज मोर ऑफ वी स्टार्टेड विद व्हाट इज़ अ रेट लिमिटर. हमें रेट लिमिटर चाहिए क्यों? कोस्ट रिड्यूस, सर्वर ओवरलोड नहीं होते. फिर उसके बाद व्हेन वी डिज़ाइन अ रेट लिमिटर व्हाट क्वेश्चंस डू वी आस्क एंड देन वी वेंट थ्रू कि रेट लिमिटर डालना कहाँ चाहिए. वी कंक्लूडेड बेटर इट इन द मिडल. फिर उसके बाद वी रेड अबाउट ऑल द एल्गोरिथम्स. टोकन बकेट एल्गोरिथम इशू क्या था, लीकिंग बकेट इशू क्या था, फिक्स्ड विंडो काउंटर इशू क्या था. जल्दी से इसे हम रिवाइज भी कर सकते हैं कि टोकन बकेट में इशू क्या था कि ईजी टू इम्प्लीमेंट तो था बट इसमें 1 मिलीसेकंड में कितनी भी रिक्वेस्ट चली जाती थी, एज एन स्पाइक ऑफ रिक्वेस्ट आता था. लीकिंग बकेट में इशू क्या था कि इसमें फिक्स्ड रेट पे प्रोसेस तो होती थी बट देयर वर मल्टीपल पैरामीटर्स टू ट्यून हियर. फिक्स्ड विंडो में क्या था कि एक टाइम स्टैम्प टी में तो कंट्रोल था बट हर टाइम स्टैम्प में कंट्रोल नहीं था, एज एन हर स्लाइडिंग विंडो में. उसके बाद वी गॉट स्लाइडिंग विंडो एल्गोरिथम. उसमें ये इशू तो सॉर्ट हो गया बट वो मेमोरी इनएफिशिएंट था क्योंकि आप सारे टाइम स्टैम्प स्टोर कर रहे थे. सो दीज वर द सेट ऑफ एल्गोरिथम्स वी रेड थ्रू. एंड उसके बाद अपन ने पूरा डिज़ाइन पढ़ा कि एग्जैक्टली होता क्या है कि क्लाइंट रेट लिमिटर को क्वेरी करता है, वो फर्दर रेडिस से काउंटर निकालता है, उस काउंटर को चेक करता है. अगर काउंटर लेस है जो उसे रूल्स में से उसने पढ़ा काइंड ऑफ डायग्राम, हाँ, तो इट लेट्स द रिक्वेस्ट टू गो थ्रू एल्स रिक्वेस्ट ड्रॉप हो जाती है. उसके बाद अपन ने पढ़ा डिस्ट्रीब्यूटेड सिस्टम्स में क्या दिक्कत आती है कि साइमल्टेनियसली काउंटर अपडेट हो जाता है. तो काउंटर जो 5 होना चाहिए था वो 4 है. एंड उसके बाद वी रेड कि वन मोर इशू दैट जब मल्टीपल रेट लिमिटर्स यूज़ होते हैं दिस वन डजंट नो अबाउट दिस एंड दिस वन डजंट नो अबाउट दिस. So they can query to a common database. That was a solution. And at end we discussed key monitoring karna is very important. So I guess that's it. It is a very good topic, as in I personally love this topic, as in designing a rate limiter. When I read this I was happy. अरे बाप रे, iPad ने भी बोल दिया बंद कर दे. चलो बंद कर देता. चलो, bye bye people. Thank you. If you have come this far, genuinely thank you.